Hello everyone, welcome to another Quad Education Test Prep Fundamentals video. My name is Tom, and today we're talking about a math topic that is explicitly tested on the ACT and then more implicitly tested on the SAT. That topic is asymptotic behavior, as well as when functions are undefined. So let's take a look.
Okay, limited edition background video number 2. So question to start off with. In math, what do we not like to divide by? In other words, what do we not like to have in the denominator of whatever we're doing? Well, you may think to yourself radicals or irrational numbers or complex numbers, and you'd be right, but there's something that we like to divide by even less. And that number is 0. Don't like to divide by 0 because it doesn't make any sense. I'm actually going to demonstrate why that's true. So first of all, we're going to talk about graphing 1 over x. So we have our function y equals 1 over x. And so first of all, we're going to say, well, what happens when x is 1? So that's going to be like right there at the point 1 comma 1. And then what happens if x is 2? Well, then x is going to be 2, and then our y is going to be 1/2. That's going to be over, and then a little further down. And then if it's 3, it's going to be a third. So 0.3, 1/3. And then what about for the point like 100? So that's going to be 100, comma, 0.01. And that means it's way out here, and it's getting closer and closer to, yes, the x-axis. And so this way is this pretty steep decline toward 0. But what about the other way? Well, what happens if we have a value of 0.5? Well, go back to many of my videos asking about what happens when we divide by a fraction, and what we do when we divide by a fraction is we multiply by the reciprocal. So 1 divided by 1/2 is the same thing as 1 multiplied by 2 over 1, which is 2. And so we go back, actually start to go up a bit. And when we divide by a third, our output is 3. So we're heading up even further. And then if we even go to something ridiculous like 1/100th, well, then our output value is going to be 100. So what this is going to start doing is approaching, as we approach 0, so this is limits if you've done this, as we're approaching the x of 0, our y value is approaching infinity because it just keeps getting bigger and bigger. So as we go to the left, starting from 1, we head off to infinity, and as we go to the right, starting from 1, we head off to 0. But then something interesting happens because, we head toward infinity, but we never quite reach our 0 for our x. But then if we start from the other side, say we said x is -1, then our output value is -1 there. And what will happen is we'll have the same sort of behavior, but mirrored across this imaginary line right here, y equals -x, mirrored on the negative side. And so this interesting shape here we have is called an asymptote, because the problem is we, from one end approach positive infinity, so going to the left approaching positive infinity, and approaching from the right side, or rather from the left side, from the negative side, so heading to the right, we're going toward negative infinity. And what the problem is here is this is not continuous, because if you go from one way, you get infinity, and you go the other way, you get negative infinity. That's a pretty big difference. That's, a difference of 2 infinity, which is the same thing as infinity, which is an entirely different discussion and very strange. But in any event, that's not very helpful because we like our results to be continuous. And what I've hopefully demonstrated here is why we can't divide by 0, because we don't know whether 1 over 0 is negative or positive infinity, which is wild to think about. So that's why we don't, mostly. And so with that explanation in mind, we're going to start to talk about horizontal and vertical asymptotes. So if I have a quick sketch of what I just did there, looks like this basically. And so this behavior where we approach a value but never quite reach it is what's called an asymptote. So this is a horizontal asymptote because it's horizontal. This is a vertical asymptote because it's up and down vertical. And what we want to be able to do is calculate what that value is at any point. And so the way that we do that is a little different for the two. Horizontal is probably the more interesting one, so we'll actually do that one first. And what you do there is you actually divide the leading coefficients. This is something that you'll almost never have to do, by the way, so don't worry too much about this. But dividing leading coefficients is just whatever is the highest order, you're going to divide one by the other. So in this case, for this function y equals 2x minus 1 over x minus 3, we're just going to cancel those x's out there, and we're going to have a horizontal asymptote of 2. And if you're wondering why these constants over to the left, or even if it's a higher order deal, like it's 2x squared minus x minus 3 over x squared, and then we would just cancel those x squares out, and we just get 2 as our vertical asymptote. Why these lower orders don't matter is because we're looking at the behavior as we approach infinity. And, if we're squaring infinity, infinity squared is technically larger than regular infinity. And so that's going to outweigh this infinity and just sort of negate it. And that's why, if we have infinity over infinity, that's going to be 1. And if we have, something larger like infinity squared or over infinity, or really even more concretely, x squared over x is our leading coefficient, then we're going to have a slant asymptote, which we'll talk about in a second. But just for your notes for the ACT, for horizontal asymptotes, you're just going to divide the leading coefficients. And another quick note there, if the order of the x is greater in the denominator, then our horizontal asymptote is always just going to be 0, because this is basically saying 1 over infinity is what we're approaching, and 1 over infinity is pretty much the same thing as 0. So just a quick note there on the asymptotes, that's to say you divide the leading coefficients. If the orders are the same, it's a constant. If the denominator order is bigger, then it's 0. And we'll talk about slant asymptotes in a moment. But first, we'll talk about vertical asymptotes. So that's that line here. In vertical asymptotes, all we do is we set the denominator equal to 0, because this is what we're looking at. When are we approaching what is the behavior of it as it slopes up and down? Where is that? Because, here in my initial graph, it's at 0, but it could very easily be someplace over to the side, like this. So all we do is set the denominator equal to 0 and factor like we usually do. In this case, I have an x squared minus x minus 12, which is just x minus 4 times x plus 3. So this, in this case, would actually have 2 vertical asymptotes, which is just fine. And that would be at -3 and 4. Okay, just like I mentioned a moment ago, let's talk about slant asymptotes. It's extremely unlikely that you'll see this. I've seen 1 or 2 questions on ACT about it, but you may. So I'll quickly say, all you do is divide, just like you do with horizontal asymptotes, and if it happens that there's a higher order number in the numerator, then you'll have an asymptote that's got a slope. So if you had something like 2x squared minus 3 over x minus 3, then your asymptote would slope along 2x. So maybe looking something like, here's an asymptote, and then here's an asymptote. It would look something like that. And so one final thing before we go into practice problems, like I mentioned at the top of the video, this is a topic that's explicitly referenced in the ACT, but more implicitly required in SAT. And so this is what I mean by implicitly required. This is more of an SAT style question. They're never going to say what's the asymptote in SAT. They're going to say something more implicit, like undefined. And that's actually almost easier if you think about it. So we have the function x minus 5 over x plus 2 times x minus 5. When is this undefined? And so you may be tempted to cancel these out. And for the behavior of the graph, that's mostly true, except for the fact that this is still in the equation. So you may eliminate it out, but the function of the equation is still something minus 5 divided by that thing plus 2 times that thing minus 5. So this still really technically exists. And so instead of it affecting the behavior of the asymptote meaningfully like it did previously, where we have a different place of the asymptote is, what this is going to produce is a hole. And you don't really need to know much about holes for the test, just that it's a little dot where the equation does not work. So for example, here we have 1 over x plus 2, which means that our vertical asymptote is at -2 and our horizontal asymptote is at 0. So if I draw a quick axis, we have -2 as our vertical, and it's along 0. So that's going to look like this. But then since we have a hole here at 5, this is going to be a little hole where it doesn't work. And in common diagrams, you'll just have a little circle in the middle of that line to indicate that a hole is at that point. Okay, as usual, we have 2 practice problems. Go ahead and take a look at that first one, and we'll see what we can do. All right, let's take a look. Which of the following is the horizontal asymptote of the function above? And for a horizontal asymptote, what we're going to do, like I mentioned, is divide the leading coefficients. So in this case, we have x at the top and x squared at the bottom. So what's going to happen is we're going to result with basically 1 over x, for which the horizontal asymptote is going to equal 0. So very tempting to provide vertical asymptotes here because we do have, x plus 2 times x plus 10 here as our factors, but that's not going to affect our horizontal asymptote at all because all we do is divide the leading coefficients for this one. Okay, now moving on to our next one, see how you can do with this one. All right, let's take a look. More open-ended with this question, I'm asking you to define the asymptotes for the following functions. So if we have a vertical asymptote or horizontal or slant asymptote. So for our vertical, that one's pretty easy. We just set that equal to 5. So our vertical asymptote is just going to be 5. And then for our horizontal or slant asymptote, we're going to have basically x squared divided by x, and that's actually going to have our x cancel out one of those x's there. So our slant asymptote is just going to be along x. So important to note that it's not going to affect the intercept. These aren't going to affect the intercept. It's just going to be along the line of x.
Okay, that's it for this video. Remember, we really don't like to divide by 0. And so tests with asymptotes and when functions are undefined will deal very much with that. So either it will explicitly ask you for where an asymptote is, or ask you when things are undefined, or when we don't want to divide by. So keep a lookout for both of those. If you found this material useful, we hope that you will like and share the video and subscribe to Quad Education. If you require any tutoring, please reach out to us. Thank you for watching, and I hope you have a great day.